Units are very important because in ecohydrology there are many different kinds of units. There are units that express areas, for example acres, square miles, square kilometers. There are units that express things like discharge rates in streams, cubic meters per second, cubic feet per second, acre feet per second, acre feet per year. And it's essential because many different agencies record data to be able to convert from one unit system to another. So even though we may not all agree that the metric system is the absolutely best system to use for measuring water or expressing measurements related to water, we have to, it's important to recognize that sooner or later you have to cope with systems that are diverse and have to be converted to a common system so that we can make sense of the information that we're getting. Before we get started, there's an important set of questions that you probably will need to answer by the time we're finished with this unit. Okay, one of them is this, is that which of the following is an example of a measurement of a fundamental dimension? Now the reason that I point this out is because a fundamental dimension, it's important to recognize what fundamental things we are actually measuring when we carry out measurements related to hydrology or ecology. The fundamental dimensions, as you'll see, include a variety of things that you'll be very familiar with, but some things that we use fundamental dimensions for are used to estimate other things. And you can see in this set of photographs we have a placard that's essentially like a ruler affixed to a bridge abutment that measures the height of the water table. We have a speedometer in the middle that actually records or measures, estimates the number of miles per hour that we're traveling at. On the far right side, you see somebody has traced a path around a garden so that they're pacing and measuring while they're pacing the perimeter of the garden, possibly to measure the area in the interior. And finally, down at the bottom we have what's called a weir, a V-notch weir, that's used to measure water flow as well. It's used to measure the flow of water in gallons per minute. Another question then is is that which of the following is a derived quantity? So the previous one focused on fundamental calculations. This one is a derived quantity. And so one of the derived quantities might be, and this is up to you to figure this out, volume calculated by length times width times height, stream discharge estimated by height of water on a ruler or a placard, like you saw in the last slide, the mass estimated by the occupied volume times the density of whatever it is of fluid, and latitude and longitude. There are two general classes of hydrologic quantities. They include basic measurements. These can be measured directly, and examples of those include, say, the height of a water surface above a specific point. Mass, kilograms or pounds. Temperature, degrees centigrade or degrees Celsius, even degrees Kelvin. And then there are also derived quantities. Derived quantities are very important because we work with derived quantities very frequently. They're not measured directly. For example, we can measure a basic measurement like length with a ruler or height with a ruler. But we can't always measure something like volume, especially when we're talking about the volume of a lake. There we have to use measured variables to do calculations that actually then give us an estimate of some other quantity. So if we take length and we multiply it times another length, say the sides of a rectangle, we come up with an area. If we then multiply that by another length in the third dimension, so that we have essentially what looks like a rectangular tank, we end up then with a length times width times height, which is a volume. And examples of derived quantities include discharge in a stream and total volume of storm precipitation. And we'll talk more about precipitation later on in the class. Fundamental dimensions include length. These are things we can measure directly. Length, mass, time, temperature. So many basic and derived quantities are expressed as either fundamental dimensions or as combinations of fundamental dimensions. Here are some commonly used combinations. They include volume. The example that I just gave was one of depth times area, or height above an area times the area itself. Volume, the units of volume are generally length cubed, for example, inches cubed or meters cubed. Depth, if we can see that we would end up with a length cubed volume by taking depth, which has units of length, and area, which has units of length squared, for example, square feet and feet for depth. Multiply them together, and we end up with a length cubed. And in the example below, if length is in meters, then length, the depth, times the length squared, which would be the area, is equal to length cubed. And if they were both in meters to begin with, then we end up with cubic meters, or meters cubed, which is a unit of volume. Some other commonly derived units include length squared, or area, length cubed, velocity, which is in length over time, meters per second, or feet per second, or miles per hour. Acceleration, length per time squared. For example, the acceleration due to gravity is 9.81 meters per second squared. Density, which is expressed as the mass, for example, pounds, per length cubed, or cubic feet, or kilograms per meter cubed. Force, they're expressed in newtons with dimensions of kilograms, mass, times meters per second squared, which are the units of acceleration, and then pressure, which are newtons per meter squared. The units are newton per meter squared. Let's derive some volume estimates from basic measurements. So volume is equal to area times height, and volume units equal length cubed. Could be feet cubed, could be meter cubed. And here's a very common measurement used in Nevada, especially when we talk about agriculture and water rights. If we have a 10-acre field and we flood it with 10 inches of water, how many acre feet of water have we applied? Well, it's important to remember one thing. An acre is a unit of area. Feet is the depth to which water is applied on that area. So if we take acre, which is our unit of area, and we multiply it times feet, one of the things we see is that we have then automatically come to this unit of volume, or this set of volume units, which is acre feet. In this case, though, we're given information about the area, acres, and we're multiplying that times the depth, which is given to us in inches. So immediately, one of the things that we see is that we have to convert inches to feet to carry out this calculation. So we have to express all the variables in the units have to be compatible with our desired result. We know we want acre feet, and we have quantities given in acres and inches. So we have to convert inches to feet to carry out our calculations. In this case, then, we have 10 acres, and we also have then 10/12ths of a foot. That means there are 12 inches in a foot. We only have 10 inches, so we have 10/12ths of a foot. We multiply 10 times 10/12ths, we come up with the answer, which is 10 acre feet, or 8 acre feet, given that we're applying 10 inches of water to 10 acres. The metric system is a really easy system to work in the hydrologic sciences and in ecohydrology. And it's convenient because of the interrelationships between units of basic measurement. The metric system expresses units of basic measurement by factors of 10 using prefixes and the unit. So for example, 1 cubic meter of water is equal to 1,000, or 10 cubed liters of water. And 1 liter of water is equal to 1 kilogram of water at standard temperature and pressure. That's what STP stands for. So it's important to remember relationships like this, because what we've done is we've gone from 1 unit of measurement, or volume, which is meters cubed. It's exactly equivalent to 1,000 liters of water. 1 cubic meter of water is equal to 1,000 liters of water. And at standard temperature and pressure, standard conditions, which apply for almost every single kinds of example that we would ever use in a class like this, 1 liter of water is then exactly equivalent to 1 kilogram of water, which means that if we know the volume of water, we also know the mass of water that is there. Metric system prefixes look like this. Kilo, okay, is, for example, in a kilometer, is 1,000. A kilo of anything is 1,000 of those things. So a kilometer is 1,000 meters. A kilogram is 1,000 grams. On the other side, a millimeter is 1,000th. That means 1 divided by 1,000th of a meter. It's a milligram is 1,000th of a gram. Mega, a unit we rarely use, but a mega is a million. So if we have a megagram, we have a million grams of a substance. Centa, as in centimeter, is the closest equivalent to the inch in the metric system that we have. It's 10 squared, or 100 of the quantity, and micro is on the other side of mega, is 1/1,000,000th of something. This is a unit that we would see when we talk about concentrations of chemicals in water. Here's some examples and some equivalents. In order to actually convert back and forth, and that was what the next module will be about, we have to know what the equivalent is between the unit systems. So in the metric system, 1 centimeter is the same thing as 0.39 inches. In the metric system, 1 megagram, okay, which would be 1 million grams, is the same thing as 1.1 tons, which is the same thing as 2,200 pounds. Remember, there are 2,000 pounds in an English ton. So which of the following is an example of a measurement of a fundamental dimension? Well, look at the bridge abutment. The bridge abutment has a ruler, it's a placard, affixed to it. The ruler is measuring length or height above a certain point, so that's a fundamental dimension. If we look at the speedometer is measuring two different things and combining them to give us a derived dimension. The two things are length and time. If we look at the walk around the garden, one of the things that we're looking at there is really a fundamental dimension, length, that's being translated into an area, which is a derived dimension. And finally, the weir at the bottom is measuring water flow, and it's deriving it from mathematical equations that translate the dimension of length into cubic feet per second. So this is a measurement of a fundamental dimension that's being translated through mathematical relationships into a derived dimension. So which of the following are is a derived quantity? Well, volume can be calculated by length times width times height, each of which is a fundamental dimension, but volume itself is a derived quantity. Stream discharge estimated by height of water on a ruler, we saw that in the last example. The height of water on a ruler is a fundamental dimension, but stream discharge is a derived measurement. Mass estimated by occupied volume times density. The occupied volume is in itself a derived quantity. And density is also a derived quantity made up of two different dimensions, mass divided by volume. And so mass estimated by occupied volume is definitely a derived quantity. And latitude and longitude, well, latitude and longitude are not measured directly as in measurements of length. Latitude and longitude are actually measured, are derived from angles and several other fundamental dimensions, and so neither is a fundamental dimension in itself, but rather a derived quantity.